All right, welcome to video 2 on related rates. You may have noticed that my previous video was a little bit different. I actually recorded myself teaching because I got behind on making videos, but I thought it went well, so I just left it up. I may make a Jamboard video later on, but what I want to do right now is I just want to work through another example of a related rate problem. And this one's going to be slightly different in that we're going to have a conical tank. A quick reminder of our strategies page. Strategy number 1 is close reading, pulling out, highlighting, pulling out information, et cetera, et cetera. Strategy 2 is modeling. And typically that involves drawing a diagram to start with, and then just listing every equation that you could think of that might relate to that diagram. Strategy 3, writing an equation, a little bit related to the modeling, but choosing out the equation or equations that specifically include the information you have and the information you need to find. Step 4 of the strategy was differentiate with respect to time. With respect to time, WRT, the abbreviation with respect to. And pretty important there, remember, use that chain rule. If a variable is changing with time, then you need to have a d-variable dt at the end of the derivative, that particular derivative, and that's true for every changing variable. Step 5 was plug values back in. Plug your constants, plug your all the different values that you had. So you're substituting all your various values. And step 6 was interpret, and this is pretty important, not just for the purposes of testing or class. This is really the whole point of doing the math in the long run is going to be to then take your conclusion and be able to go to somebody and say, okay, here's the scenario, here's the answer, this is what you should or should not do. So in interpretation, don't forget to use units, be specific, et cetera, et cetera. So we have a conical tank for this particular example. We have water running in at 9 cubic feet per minute. The tank dimensions are 10 feet high. Sorry, this is tank. That's an N, and that's an A. 10 feet high and has a 5-foot radius. I'm not writing very well, probably because I'm trying to write so small here. And the question we have is, how fast is the water rising? At a depth of 6 feet. So when I look at this, let's start by doing some modeling. First of all, water running in is a change in volume. So we could say that the change in volume with respect to time, and it's running in, so that's positive, 9 cubic feet per minute. We know that if we label this with an H and an R, that H is equal to 10 feet, that R is equal to 5 feet. But now I've got another situation here where I have the actual water in the tank, which is also going to be conical. And this is 6 feet. And I'm interested in, let's call this small d depth. I'm interested in when small d is equal to 6 feet, and I want to know the derivative of d with respect to time. So, what else do I know here? Well, I know that this cone of water also has a radius. I'll call that R2. Maybe instead of D, I should have called that H2. How about let's go back and change that. Just because DD is awkward. Now we'll call this H2, and so the derivative of H2 with respect to time is my unknown. So what have I got here? I've got volumes, I've got heights, I've got radii, everything's a cone. And let's just focus on the water for a minute. I know that the volume of a cone is 1/3 pi r squared h. And of course, this is not the 5 and the 10 because I'm interested in the cone of water. So I'm going to put a little subscript on this. A 2 to remind myself I'm dealing with the water here. But I also know that radius right there is related to the size of the tank. I know that 5 is to 10 as the radius of the water is to 6. Because if I think of this as right triangles, let me draw a right triangle on here. I've got 2 right triangles here, one for the whole tank and one for the water. And so that means that, you know what, I need to change that. I'm going to quickly erase something. It's not 6, and I made one of the classic blunders. It's that right there. The radius to height ratio of the water is going to be equal to the radius to height ratio of the tank because of similar triangles. So let's go ahead and substitute. I know that R of the water is equal to 1/2 height of the water. This tells me that the volume of the water is 1/3 pi times 1/2 h water squared times the height of the water. Doing a little simplifying, I've got volume is equal to pi over 2 squared is 4. That's 12 h of the water cubed. And now I can take the derivative. Step 4 with respect to time. The derivative of volume with respect to time is equal to, well, pi over 12 is a constant, times, well, 3 times the height of the water squared times, chain rule says, height of the water with respect to time. I know that this is 9. I know that this is 6, and I can solve for that. So, the rate of change of the height of the water with respect to time equals, well, I've got 12 times the rate of change of the volume divided by 3 times pi times the height of the water squared at that time. And if I type that into my calculator, I get approximately 0.32 feet per second. So, a couple things we need to take into account before we get to step 6. And that is to be very careful. Once again, I just want to remind, don't substitute unless you're sure something is a constant. If something is not changing, you can go ahead and substitute. If it's got a rate of change associated with it, do not substitute. One of the examples that I gave yesterday was the police car example. The base of the triangle is 500. No, I take it back. Not the police car, the balloon example. The base of the triangle was 500 feet, and it wasn't changing because the observer and the launch point of the balloon were not moving. They're relative to each other. So it was okay to put in x equals 500 because there's no dx dt. In this case, we have a dVdt. We don't want to put in our volume, even if we knew it. We've got a dHdt. We don't want to put in h. And then r we're writing as a function of h, and so it doesn't really matter what the radius is. All right, finally, let's get to the interpretation. The height of water in the tank is increasing by approximately 0.32 feet per minute. I don't know if I said minute or second on the previous page. I said second. Yep, I meant minute, of course. When the water height is 6 feet. This is really important. When the water height is 6 feet. And the reason that this is important is because it is not always increasing at 0.32 feet per minute. As the tank gets wider, it's going to slow down. As the tank was narrower, it was going faster. But we were very specifically asked, well, what about when the height is 6 feet? So we have to be a little bit careful that we specify this is when that 0.32 feet per minute is actually a legitimate answer. Okay, if you are in my class, why don't you go ahead and do exercise 17 in the book. And we are done with the section, but I'm going to do more examples. So you will, if you come back here, if you're following along in the book, you'll notice that we're done. There are no more related rates problem examples in the book. This is a fairly complex a process, just because there are so many steps and because it's so important that you get the model right, which means the equation right and the derivative right, substituting at the appropriate times. And people do tend to struggle as there's a lot of very complicated problems involved in this. So what I'm going to do is I'm going to come back with probably 2 more videos of nothing but related rates examples, some of which will be off the AP Calculus test. So hopefully we'll see you then. Thanks for watching.